This is an example from section 6.4 on the central limit theorem and section 6.3 sampling distributions. So in this particular problem, we're told that an engineer wants to redesign some seats for an airplane, and the seat is designed for pilots weighing between 140 and 181 pounds. And we're also told that the population of pilots has normally distributed weights with a mean of 147 pounds and a standard deviation of 31.1 pounds. Anytime that you read a problem and you're told that your data is normally distributed, immediately I want you to draw yourself a bell-shaped curve, which represents the normal distribution. At the center of the distribution is where we find the mean value. So here that's 147 pounds. And I always write this information off to the side somewhere. So mu is 147 pounds. And sigma, which is the population standard deviation, is 31.1 pounds. Okay. Now, in question A, we're asked if a pilot is randomly selected, find the probability that his weight is between 140 and 181 pounds. So when we take a look at this bell-shaped curve that I have below, this is a probability distribution for heights. And so from the population, every single x value that makes up this distribution, each x represents a height, right, for a pilot in the population. So I can't draw all the X's, but I want you to imagine that I collected data from the population of all pilots and then measured their weights and plotted it. So this represents all the weights of every single pilot from this new population. Okay, and then we find out that their average weight is 147. So that's at the center. And so to answer question A, let's mark, so if the average or the mean weight is 147 pounds, let's mark where 140 pounds is. And again, it doesn't have to be to scale, right? I'm not really sure where 140 is. I just know it's less than 147 and 181. Okay, again, I don't know where 181 is on this distribution. I just know it's more than 147. And so question A wants us to find the probability that one randomly selected pilot, all right, selected from this distribution, is between 140 and 181 pounds. So that probability is represented by the red shaded region under the curve, which I shaded in red here. So in red, if we can calculate that area under the curve, this area gives us the probability that one, and I'm emphasizing one here, randomly selected pilot weighs between 140 and 181 pounds. So if you're using your calculator, this is where you would use normal CDF. So if you're using your TI-84 calculator, normal CDF is going to ask you to put in your lower limit, which here would be 140. Your upper limit is 181, and then you're going to put in your population mean, which is 147, and your population standard deviation, which is 31.1. And then when you press enter, so I actually have to do this problem. Give me a second to put it into my calculator. You can put it into yours as well. And the calculator tells us that that is approximately 0.452 if I round to 3 decimal places. So that means that there is about a 45.2% chance that if I randomly choose a pilot, that pilot's weight is going to be between 140 and 181 pounds. Or we typically write our probabilities as a decimal. That's 0.452. Okay, so that's how we would answer question A. Now let's take a look at question B, and I want you to pay attention to the difference between question A and question B. In question B, it says, if 36 different pilots are randomly selected, what is the probability that their mean weight? So here I want to know, all right, what is the average or the mean weight of 36 pilots? That the average weight of these 36 pilots is between 140 and 181 pounds. So in question B, we're no longer looking at just the distribution of weights of pilots. We're looking at a sampling distribution, okay? So in question B, the sampling distribution, we learned from section 6.3 that anytime you have a sampling distribution of sample means, the sampling distribution for sample means is also normally distributed. So it's also normally distributed. But this distribution is not made up of x's, where x represents the weight of a pilot. This distribution represents a bunch of x bars, where x bars, right? So what we do is we take a look at the population So imagine that the population is the weight of all pilots, okay? And then we randomly select from that population, we randomly select where N is 36, okay? So we randomly select 36 pilots, and then we take the average weight of all 36 pilots. So out of 36 pilots, let's say that their average weight is some X bar. And we take that X bar and we plot it on a distribution. So just imagine repeating this process many, many times. So from the population, I keep taking samples of the same size. So 36 pilots, I write down their weights and then I average it. That gives me an X bar and I plot it on the distribution. And then I take another sample, another random sample of 36 more pilots, and I calculate their average weight. And again, right, it might be a different X bar, or it could be an X bar that's similar to a previous sample. But the idea is that we get a distribution that is made up of a whole bunch of X bars, where each X bar represents the average weight of 36 pilots, okay? And so again, this distribution is normally distributed. And what we learn in section 6.3 is that when I take the average of all the average weights, meaning when I take the mean of all my sample means, the mean of all of my sample means ends up being really close to the population mean. So by the central limit theorem, so the central limit theorem says that anytime I have a sampling distribution of sample means, right, the mean of all my sample means targets my population mean, okay? And then the central limit theorem also says that the standard deviation of all of my sample means approaches the population standard deviation divided by the square root of n. So here, to answer question B, if I want to know what is the probability that if I were to choose 36 pilots at random, that the average of their weights is between 140 and 180 pounds, I'm looking at the area of the shaded region that I just shaded here, but this is saying what is the probability that not X, but X bar is between 140 and 181. So I hope you can see the difference between question A and question B. So we have to use the central limit theorem here to answer this. And so again, because this is a probability and it's on sampling distributions are normally distributed, right? I can use normal CDF on my calculator. So if you're using normal CDF, your lower limit is still going to be 140. Your upper limit is still going to be 181, right? And the central limit theorem says that the mean of this sampling distribution is equal to the population mean. So this means that I can use 147 as well. But I cannot use sigma in the same way that I did in part A, because the central limit theorem says that the standard deviation for sample means, right, it's not sigma, but it's sigma divided by the square root of n. And so guys, I'm kind of running out of space here. But on your calculator, you would type in 31.1 divided by the square root of 36. So if we do this, again, go to your calculator and then go to your distributions and choose normal CDF. This time you have to adjust the standard deviation sigma so that it's 31.1 divided by the square root of 36. And when you press enter, it's going to give you a pretty large probability, 0.9116. All right. And it makes sense that your chances, or the probability that the average weight of 36 pilots being between 140 and 181 is high as 0.9116. That makes sense because already we can see here that approximately 0.45%, all right, there's a approximately 0.452 probability, or a 45.2% chance that if we randomly choose one pilot, right, let alone 36 pilots, that his or her weight is going to be between 140 and 181 pounds. All right, so that is the difference between a normal distribution for a random variable such as weight versus a sampling distribution of sample means, where we're looking at the average weight of n number of people or objects.